I'd like to welcome everybody to the second DIDACT Symposium, sponsored by the Trial Innovation Network and aiming to improve generalizable knowledge about clinical trials and clinical trial methodology. The TIN, in its second version, is attempting to bring as many institutions as possible into this concept of developing clinical trials as a multi-institutional task as opposed to a single institutional task. And both the Vanderbilt Trial Innovation Center, the Hopkins Trial Innovation Center, and the Vanderbilt Recruitment Innovation Center are organizing their awards towards this goal of expanding expertise and expanding inclusivity in clinical trials. And today we have a very interesting program for you that Guyan will walk you through. I'm Dan Hanley, the PI of the Hopkins TIC, and Guyan will introduce herself, and we're going to be your moderators. Guyan?
Sure, thanks, Dan. And I'm Guyan Yanoukian. I'm a senior scientist in the Department of Biostatistics at the Johns Hopkins Bloomberg School of Public Health. I co-direct the BIRD, or Biostatistics Epidemiology and Research Design Core, within the Clinical and Translational Research Program. I'm also a member of the JHU Trial Innovation Center. And so here you have the agenda in front of you. We have, as Dan said, very, very exciting talks lined up. And so thank you to our panelists for agreeing to support the program and to give these talks today. So Dr. Ravi Varadhan is a professor of biostatistics and oncology with joint appointment at Johns Hopkins Bloomberg School of Public Health and School of Medicine. His research focuses on multiple areas, including characterizing physiological underpinning of frailty and resilience in older adults, heterogeneity of patient-centered outcomes and comparative effectiveness of intervention, cross-design synthesis to combine both randomized controlled trial and registry data for valid inference for groups underrepresented in trials, as well as fast and efficient computation in complex high-dimensional statistical modeling. Dr. Varadhan has developed several open source software tools for computational statistics and numerical optimization. And so today, he's going to talk about individualized treatment effects using flexible Bayesian modeling approach. So thank you, and looking forward to the presentation.
Thank you, Guyan, and thank you all for joining this afternoon. Today, I'll be discussing a modeling approach that we have developed over the past few years to characterize variation in treatment effects, or what's known as heterogeneous treatment effects from clinical trials. That was the original setting in which we were motivated to do this, but it could also be adapted to observational settings where the treatment is not assigned by the investigators. So we will be discussing a flexible approach using a Bayesian framework. I wanted to just acknowledge my collaborators on this, Dr. Nicholas Henderson from Michigan and Daijiro Kabata from Japan. So I hope everyone can see my slides and also hear me properly. Okay, thank you. Okay, so I always start with this one. It's one of my favorite quotes where David Mant in Lancet, he put it very nicely. The paradox of the clinical trial framework is that it is the best way to assess whether an intervention works, but it is arguably the worst way to determine who benefits from it. So in a way, it's as though the trial framework is set up to examine the intervention, not focused on the patients per se, right? Of course, that's kind of an overstatement maybe, but there is a lot of validity to that statement because the trials focus on the average treatment effect, right? And it's not clear whether the average treatment effect is valid for everybody in the trial. So now the notion of heterogeneous treatment effects has been gaining a lot of traction. There have been a lot of tools that are under development for exploring heterogeneous treatment effects. And so my definition of heterogeneous treatment effect is that which refers to explainable variation in treatment response that's attributable to patient level variables. There could also be important heterogeneity in process level variables, such as the healthcare system or the physicians and so on. So it could be thought of as a multi-level phenomenon. But for my discussion, I will just focus on factors that are attributable to patient characteristics. So this problem of HTE, heterogeneous treatment effects, there can be variety of questions that can be asked under this broad topic of HTE. And particularly, I want to say that it goes beyond what is typically known as HTE, which is subgroup analysis, right? And also a little bit more general version of that, which is treatment covariate interactions, right? So the HTE questions can be broader than just these two topics that are relatively well known to statisticians. For example, we could ask questions such as, what is the overall degree of heterogeneity in the treatment effect in the trial? Is that relatively homogeneous or is there considerable heterogeneity in the trial? And we could also ask, what's the proportion of patients who benefit from the treatment? Or we could be interested in qualitative interactions where certain groups of patients are, they have the wrong sign of the treatment effect. So if you're looking at treatment versus controls, then it is the treatment is harming the people. But if it is a comparison of two active treatments, then qualitative interactions are, they just mean that one treatment's better than the other in one group, and the other group, it's the other way around, right? So this qualitative interactions are kind of interesting, whether you're in placebo-controlled setting versus active control. Okay. And then you could also do estimation of individualized treatment effects, not individual treatment effects, but individualized, because individual treatment effects are clearly not identifiable, whereas individualized treatment effects are sort of model-based or based on assumptions. And then prediction would refer to individualized treatment effect in a future sample or future set of patients, those who are not in the data set that's being analyzed. And then you could also ask, what is the optimal allocation of treatments to individuals, right? So you can look at the estimates of each individual under different treatments and then rank them and then determine the optimal allocation. So there are many questions. This is not by any means an exhaustive list of questions. So why a Bayesian framework? So the phrase heterogeneity of treatment effect implies an underlying distribution of treatment effects. So in that sense, a Bayesian framework seems natural because in this, we look at all the unknowns as random variables. And so we could think of treatment effects also as random variable, and then look at the distribution of treatment effects. So Bayesian framework would seem natural. And also, there is more emphasis on estimation of the variation or heterogeneity rather than a binary setup of hypothesis testing. Typically, in subgroup analysis, we end up in a binary setup. Is there heterogeneity or not? Is subgroups differ? If you, or in a more common setting where they would do interaction tests. And if the interaction test is significant, then you report group specific treatment effects. And if the interaction test is not significant, you don't report group specific. So such sort of dichotomous decisions are avoided, and you could just do an estimation of heterogeneity. And then the question just becomes, is that important enough or not? Right? Is the heterogeneity actionable? Is it important? So that's the question, rather than is there heterogeneity or is there no heterogeneity? Right? Because no one truly believes that there is absolutely no heterogeneity. Okay. And so this Bayesian framework is also suited to estimation with many parameters, right? And if you're in a subgroup setting, you could have subgroups with very small sample size, and they would have treatment effect with huge variances because of the small sample size. But a Bayesian framework in that setting would do what's known as shrinkage estimation. So it would shrink the treatment effects towards the average treatment effect. And thus, and it also applies to the situation that I'll be describing, the individualized treatment effect, and it tends to prevent overfitting. And also an important point is Bayesian framework doesn't necessarily mean that everything is subjective. You could actually set up your prior distributions in a way that the resulting procedure has good frequentist properties, right? I will show that. So you could think of it as more of a way to come up with procedures rather than looking at it from a subjective point of view. Okay, and a few more advantages. I'm sounding like a salesman for Bayesian, but so I hope I don't sound overzealously pushing Bayesian. Yeah. So Bayesian framework can support direct probability statements. So you could actually ask, what's the probability that a given individual benefit from a treatment, right? So these questions are a little bit hard in a frequentist framework. Like you can imagine those who have had the difficulty of explaining confidence intervals to lay people would understand, how easy it is to explain that in a Bayesian framework as credible intervals, right? So it's much easier to answer questions that a layperson would have. Do males get more benefit than females? And so on, right? You can ask all these questions and get answers in terms of posterior probabilities, right? And then you could also bring in multiple outcomes like benefit harm variables and then combine them together and obtain the posteriors for different combinations of benefits and harms and so on, right? So there are many advantages. Okay. So let's talk a little bit about how we will model heterogeneous treatment effects, right? So in contrast to subgroup analysis, because we are asking more ambitious questions here, we need a sufficiently rich modeling framework, right, to answer these more ambitious questions, right? And we believe that Bayesian non-parametric approaches, I will explain what I mean by non-parametric shortly. They are well suited to provide this kind of individual level view of heterogeneous treatment effect, right? And the non-parametrics can also help us to construct flexible models for patient outcomes where all the unknown quantities have probability distributions associated with them. And so it'll be the usual Bayesian way of generating posteriors, samples from posteriors for all the unknowns. And so then we can focus on the unknowns that we are interested in. So the motivation of our work is to develop a flexible, non-parametric approach that can address many of the HTE goals. Okay, and so I'll start with some notation, and just want to mention that we are applying this framework in a survival analysis context, where the data is time to event, the primary outcome is time to event, right? BART has been used previously in continuous outcome settings or in, mostly continuous outcomes. I don't know if there's version of that for binary, but so here we are extending BART to time to event outcome, which are subject to censoring, right? And so the notation is that we have capital T for time to event outcome for the patient or subject in the study. And A sub I is the assignment to different treatment arms. And then we have the potential values for the failure times under different treatment assignments. And then we have the actual time under the assignment T of A, which can be given as the combination of the potential values. And so even though T is the actual failure time, we don't usually have the opportunity to observe that on everybody. So instead, what we observe is this Y, which is the minimum of the latent or actual failure time, and their follow-up censoring time, right? Where the observations are censored due to the termination of the study or for reasons where the subjects don't participate in the entire study, right? So we have censoring, and then we have an indicator that tells whether the subject was censored or not. And we have a rich set of baseline covariates, right? So when I talk about individualized, basically I'm talking about these X's, right? This X is what denotes an individual, right? You could go as deep as you want or as shallow as you want. Like in a subgroup analysis, it'll just be usually a one-dimensional covariate, right? Binary or categorical, but you could be very rich in terms of the characterization. So we'll assume that the patients are randomly assigned to the treatment arms. Although this is, as I was saying in the beginning, the method can also be applied in observational settings with the addition that you may want to incorporate some like a propensity score or something into this Bayesian model as an additional covariate. And in fact, that has been done, and I will briefly say that in one of the slides. Okay. So the model that we use for describing the failure times is accelerated failure time model, rather than the more well-known proportional hazards model, which models a hazard function. Whereas here we directly model the failure time itself. It's actually the log of the failure time. And this is the standard AFT model, which is parametric. Log of T is X transpose beta plus an error term. But instead of this, we would take a more general version of that. So where log of T is represented as a regression function, right? Plus an additive, so there is an additive error term. And the error term is assumed to have a zero mean. But apart from that, we don't make any real restrictive assumptions about the regression function or the residual error term. So it's reasonably general. And as I was saying before, in contrast to the Cox model, the AFT models directly look at the survival time. So in some sense, they are more interpretable than the hazard function based models, right? So for example, the treatment effect is easily interpretable. There's a difference. Well, easy is a function of who is interpreting it. So uh, expected value of log survival time, I'm not sure how easy it is, but but the treatment effect is a difference in expected value of log survival time, or maybe a little bit easier, it's the ratio of expected survival time, right? Because I'm not sure how interpretable log survival time is. Yeah. Okay, and once the model is fit, we can calculate the individualized treatment effect for an individual with covariate vector X as the difference between the expected log failure times, like shown here. Theta of X is the expected value of log T given the covariance X for those in the treatment arm minus the expected value for those in the control arm, right? Actually, this is sort of like a counterfactual, but it's model based, so we can actually calculate it. Same person X is assumed to be under A equals 1 and under A equals 0, right? And so it can be written as this regression function m of 1 comma x minus m of 0 comma x, right? If you go back to the previous one, the definition of regression function here, m of a comma x, I will talk briefly about how this m is actually estimated. Okay. So this is the individualized treatment effect. Here it's shown as the difference in the expected values of log failure time. But it can also be written as the ratio of expected failure times, right? Rather than differences of logs, here's a ratio of the raw failure times. Okay. So getting back to the regression function, which is one of the main components of this, it's basically a collection of these regression trees. Like one such tree is shown here, right? Here there is a tree with two splitting variables and 3 terminal nodes, right? And each terminal node has the expected value of log t or whatever it is, right? And so these trees are added together to form the totality of this regression function m of a comma x. There's a lot that goes on here. You have to figure out how to select which variable to split on and what value to split on and what depth you need to keep going with regards to the splits. So there are a lot of decisions that are made. And for each of these decisions, we have a prior distribution in a Bayesian framework, and they're relatively non-informative. Okay, for example, the covariates selected would be uniform distribution from the prior. The prior would be uniform, and the split value would be uniform, and so on, right? So we would basically let the data drive these things. Okay. So here is an example. It's very simple example that shows how BART works, right? So suppose you have the true function, regression function like this, a dark, continuous, smooth line. And then the tree that I showed before, it had 3 splits, 3 terminal nodes. So it'll have a stepwise function with 3 jumps in it, right? Whereas if you do a BART with, let's say, 200 trees or 500 trees that are added together, you will get a function like this, which has little discontinuities, but it's a lot smoother than a single tree, right? And it tends to hug the true value pretty well. So So this is just a simplistic picture of how BART might work in a one-dimensional case. Okay. So advantages of these Bayesian additive trees is that they've been shown to provide pretty competitive predictive performance, right? There are more and more examples that are emerging now that BART tends to do well, pretty much as an off-the-shelf method, right? Even though there are a number of hyperparameters, I don't want to oversell it. I mean, it's possible that there are scenarios where the default settings of the hyperparameters may not be the best ones, and you may need to play with them. So that would require a deeper understanding of what is going on. But in general, it has been shown that the default settings that are established tend to do reasonably well, right? So it could be used as an off-the-shelf method, right? And it's good at handling interactions and nonlinearities in continuous covariates, for example, right? And to me, the next one is the main advantage. It automatically provides measures of uncertainty, despite the complex nature of the model. This is very huge, right? I'll show you some example of this. And it has the potential to be incorporated into more complex Bayesian models, like you want to introduce random effects or spatial variations and so on, right? So I talked a little bit about the mean regression function, but let me also say a little bit about the additive error term, W, the residual. So it's assumed to be smooth, and the density of that residual is, we model it as a location mixture of Gaussian distributions. So the phi is the standard Gaussian normal density, and there is a location parameter tau that is mixed using a Dirichlet prior, and sigma has its own prior, right? But it's in our formulation, one of the restrictions is that it is a homoscedastic model. The sigma is not allowed to vary with x or things like that. So that's probably the only non-flexibility of this model. Apparently, there is a recent paper that came out that relaxed this assumption. Okay. And the residual distribution, I'm just showing some examples here. They might look like this. So here's just one location parameter. Here there are 2 or 3 locations that are mixed, right? So you can increase a number of mixtures in that location, the Dirichlet process model, and you can get residuals that can conform to more complex data settings. Okay, and this is the full model. Okay, you have the main model log of t as a regression function plus an additive error term. And the regression function is a BART, which is a sum of trees. And these parameters, which I'm not going to go into detail, they basically describe, like what I was talking about, how to choose the splits, which variables to choose, what depth to go into for each tree. Those are determined by alpha and beta. And K and H are parameters that look at the prior distributions on the values at the terminal nodes. Okay. And then here is the specification for the residual term, W. And again, it's sort of a hierarchical framework here. W given tau and sigma squared is normal, and then tau is modeled as a Dirichlet process with measure G, and G in terms is modeled as a centralized Dirichlet process model. The centralized process basically ensures that the expected value of W is 0. The regular Dirichlet process doesn't have that property, okay? And then the sigma squared has an inverse chi-squared type distribution, and so on, right? So you can see from here that there are a number of hyperparameters, alpha, beta, K is an important one, and so on, right? And so a lot of the work actually, there was a paper by Chipman, George, and McCullough in 2011. They did a lot of the heavy lifting initially for these sorts of parameters like alpha, beta, K, and so on, right? So there's not much novel that we are contributing to this here. Maybe that we're using the centralized Dirichlet process to do that, and there are some tweaks that we applied to in terms of the centralized Dirichlet process. But apart from that, it's mostly standard BART. Okay, so we don't take credit for a lot of this actually. And details as to where we follow Chipman, George, McCullough formulation and where we deviate from that, you could refer to our paper in Biostatistics 2020. I have it in the reference list. So all the details are provided there for the prior specification and also how the posterior sampling works. Okay. So the posterior distributions of all the parameters, as well as the random variables of t, can be generated, and it can be used to answer a variety of questions. For example, we can look at point estimates and interval estimates of individualized treatment effects, also known as conditional average treatment effects, CATE. And you could look at the histogram or the distribution of individualized treatment effects. And I already mentioned many of these: proportion of patients expected to benefit from the treatment. You can explore qualitative interactions of interest, for example, male versus female, or whatever disease characteristics, people with disease characteristic versus not, whether there is any qualitative interactions there. Right? So you could do a lot of different things with the posterior distributions. And we have an R package that's been out there for a few years. Right now it's on GitHub, but we are working to put it soon on the CRAN repository. So there is this library AF trees, and the usage is very simple. You just give the covariate or the design matrix and the observation time y, and then the censoring status 0 or 1, and the number of posterior draws, right? There are a lot of hyperparameters, as I said. You can look at the help file to see which hyperparameters you want to play with. It's always a good idea to vary the hyperparameters to see how sensitive the results are. For example, there are a couple of hyperparameters which I mentioned, K, which basically describes the variance of the values in the terminal nodes. So if you play with K, the prior can become more or less informative, with regards to the failure time distribution. So that's one value that we recommend that people play with. And we have seen that the other hyperparameters are relatively insensitive, but there is obviously no guarantee that they're insensitive in all problems. Okay, I wanted to show some results. So here is a paper that came out recently by Fan Li and others, which compared different machine learning methods for heterogeneous treatment effects in observational data for survival setup, survival treatment effects. And they basically said that a non-parametric Bayesian additive regression trees with the framework of AFT consistently yields the best performance in terms of bias, precision, expected regret, right? So it's not just my claim, but it's been shown by others independently. And also, this is an important point. The credible interval estimates from BART provide close to nominal frequentist coverage for the individual treatment effects. And I will show that we are doing our own simulations. Actually, Fanli's simulations, she compared a lot of machine learning methods, deep learning, random forests, and so on. But she didn't include this one, causal survival forest. It's a relatively recent one, came out in 2023. And this is becoming a very popular method. So we thought, if we can beat the most popular one, then ours should be the best, So we compared causal survival forest to BART in terms of bias, RMSE, misclassification, and coverage rates. And we use different data generating mechanism. This is something which I kind of want to emphasize a little bit, that normally when people do simulations, obviously you choose the settings, right? So your method will always look better. You're not going to show settings where your method is much worse than the competitors, right? There's always a bias in reporting. So what we did was we chose simulation settings from different papers. Fanli's paper, our paper, and the causal survival forest paper, right? So one is like our setting, the other is competitor setting, and the third one is a neutral setting, right? So I mean, there's a lot of stuff in here, right? I mean, it'll take me a lot of time to go through this, which I'm not going to do. But one of the main things I wanted to point out is that the coverage rates for BART tends to be better than the coverage rates for causal survival forest, right? And also the misclassification rates are generally lower for BART compared to causal survival forest, okay? And we show the results for a couple of different values of hyperparameters, the ones that we think are most sensitive in BART as well as the causal survival forest, okay? In terms of bias, in some settings, the causal survival forest tends to do better than BART. But in terms of coverage, BART seems to do better than causal survival forest, right? And in the setting of Kozarok and Sui and Susan Athis, there also we see that the coverage rates are not that great for causal survival forest. For some reason, we don't really understand why. So we're actually going to look at data extrapolation issues. Maybe there are individuals where there's not much data for treatment effect in those neighborhoods. And so we're kind of looking into trying to explain this coverage rate phenomenon, okay? And then this is our paper setting where BART is clearly better than causal survival forest, okay? How much time do I have?
I think 10 minutes.
Okay, great.
There is
So-
one
so-
though, so we can see when we take it.
Okay. So in summary, the simulation results show that BART tends to do better than causal survival forest in terms of coverage rates for sure. And misclassification rate also seems to be better. In some cases, the bias is better for causal survival forest. So that's the summary of our simulations. And I will close with an actual data example. This is from an old cardiovascular trial for ACE inhibitors. This was back in the 90s. So it was for looking at ACE inhibitors for people with either congestive heart failure or people who are at risk for congestive heart failure. So there's a prevention trial and a treatment trial. And so there were 2,500 plus people in treatment trial and 4,000 in the prevention trial. And the endpoint was a composite endpoint, time to death or time to hospitalization. And we have data on 18 baseline covariates. And in the trial, the treatment effect, the overall treatment effect was very strong and highly significant, right? And so we wanted to explore if there was heterogeneity in this trial. So here are the individualized treatment effects, right? And here I'm showing the theta effects as I define, which is the difference in the expected log failure time, right? So if this value is positive, it implies that the ACE inhibitor is working better than the placebo. And if it's negative, it's the other way around. So there is a very consistent effect of the treatment effect. There are just a few very small number that has a point estimate that is negative. But even there, the confidence interval was fairly wide. So overall, it seems like the treatment is doing consistently well. And there should not be a lot of heterogeneity in an important sense, right? Even though there is quantitative heterogeneity, right? But there is no essential heterogeneity, if you want to call it that, right? And here is a histogram of the treatment effects. We kind of split it into the two trials. The treatment trial tends to have a stronger treatment effect than the prevention trial, but both have reasonably strong treatment effect, right? And here we presented the treatment effect as a ratio rather than difference of expected survival. So one would correspond to the vertical line here shows the no effect. Okay, so majority of the people are to the right of that. And here are individual specific posterior survival curves, right, from the BART model. And then we average the individual survival curves in the two groups. And that's shown in the solid line. And then the dashed lines are the Kaplan-Meier estimate. So there is good agreement there between the Kaplan-Meier estimates and the average of the individual estimates. We could calculate the proportion benefiting also as is sum of these indicator functions or those for whom the treatment effect is positive, right? The theta is positive or the z variable is greater than 1. This is the ratio variable, okay? And so you can estimate Q. Actually, you can take the area under that histogram that I showed before, right? And that'll be an estimate of Q. And it turns out that the estimated proportion of patients benefiting is 96% in the treatment trial and 89% in the prevention trial. So I think these kind of estimates could be very useful. If you see a trial where proportion of patients benefiting is like 50% or something like that, you would be concerned that there is a lot of heterogeneity in the trial. So here is another way of showing that. So what's the proportion of patients with a positive treatment effect with the posterior credibility of 99% or more? So you are very sure that these patients are getting a benefit. So there's 51% of the patients who have very strong, highly credible benefit. And if you lower the credibility threshold to 95%, then you have a total of 75, 76% that are getting benefit. So you could break it down in this way and show the heterogeneity as well. Or you could look at evidence for differential treatment effect. A differential treatment effect is where the theta is greater than or equal to the average theta bar. And then you could define one that is agnostic to the sign, whether it's greater than theta bar or less than theta bar. So you could define as 1 minus 2 times this d, and you can calculate the proportion of people whose differential treatment effect is greater than 0.95 and so on. So here it doesn't seem to be very large, like 19% have differential treatment effect greater than 0.95. Okay. So you could do a lot of different things. And this is an important one, the qualitative interactions. So if you have particular subgroups that you're interested in and you want to see, is the treatment effect have different signs in those subgroups, right? And you can do that. So in the solved data, the probability that the sign of the treatment effect for males is not equal to the sign of the female. So they're either positive, negative, or negative, positive, right? And that probability, the posterior probability of that is 0.035. So there is not much qualitative interaction going on in this trial. Okay, and you could do variable importance plots too. This would be like sort of fit the fit kind of idea. Once you fit the BART model and you get individualized estimates, now you can use that and refit that with the covariates and try to get this sort of variable importance plots that shows for each individual variable how does it estimate or predict the difference in survivals, right? This is sort of like a post-process kind of a thing. Okay, so in summary, I've presented a flexible approach for HTE assessment, non-parametric models, and they seem to outperform causal survival forest. There is more evidence that is needed in this to make this conclusion, but this seems to be the case based on our limited experiments. The user input is minimal. From our experiments, we have seen that there is only one hyperparameter that is quite impactful, which is the one associated with the prior on the regression function, and it's called K in the R software. So there is a package, AF trees. It's very easy to use. I would encourage people to try it and give us feedback. And these are the references that I mentioned in my presentation. Thank you.
Thank you so much, Ravi. This was very, very interesting and very applied, right? So usable for trialists, and not only. We don't have too much time, but maybe just one question. Where do you see the next steps, right? What potential other scenarios, or maybe one thing comes to mind, maybe missing data for some access for certain patients.
Yeah. So like, for example, censoring itself, you could think of it as partially missing data, right?
Right.
So we have the data augmentation approach to impute the failure times for the censored observations. So that could obviously be included, extension to missing covariates, right? So the data augmentation could be expanded to include missing covariates. That's a good point. I think that would be an important addition. And then in the causal survival forest, they modeled the censoring mechanism too, as a function of covariates. So the potential failure time T is independent of censoring time given the covariates. So they model the censoring time with covariates, whereas we don't do that. The imputation is based on data augmentation. There is no explicit model for censoring. That could be an extension too. And then I talked about propensity score. You know, we've thought about propensity score. It's very easy to do. In fact, Fondley already did that. They used propensity score as a covariate in the model, right? But you could actually think of some sort of a weighting approach as well. And usually the weights and Bayesian methods don't go well together because of it's based on likelihood. So when you bring in weights, it just kind of makes it more complicated. So you have to work with the different loss functions then. But we are also thinking about that using a weighted propensity score and extending the Bayesian framework there. So there are such directions, I think, and
We have one other question that maybe the quick answer to, it's in the chat from Jeff
okay.
Hornbein. How is BART related to random forests?
Yeah, I mean, so random forest, it doesn't treat the trees as random variables, right? Even though it says random. But I mean, it's random in the sense that the data is sampled, you know, and then you build a tree, then you sample and build trees, and then you sort of aggregate them, right? This idea of bagging. But it's not random in the sense that you have a distribution and you could put priors on that distribution and so on, right? So it's a different way of looking at this. And in fact, with random forests, you cannot get uncertainty estimates that easily. I mean, you know, the only way that I can think of is maybe there are methods now that people are working on to get interval estimates for random forests and things like that. But it's not easy to do that. Whereas in a Bayesian setting, because it's truly random, the BART nodes, the BART splits, and so on. So it's easy to generate posteriors for all of these things. And we
Great,
can get
great.
confidence intervals or credible intervals.
Okay. I think the next round of questions we'll do at the panel